Nina's here to open WIDEX Audiological Summit with a biological perspective on listening difficulties. Nina will talk about auditory processing and experiences and how training the hearing brain holds the key to successful hearing. So please join me in welcoming Nina Kraus.
Good morning. Thank you for the introduction. I'm very happy to be here, and I hope that folks will move down and come close to me because I came here to be with you. So I get to talk about one of the things that I care so much about, which is our life in sound. And I'm a biologist, so the biological perspective is meaningful to me, and I hope to you. Making sense of sound. The grass is moving, and the animal has to figure out, should he run? Should he stay? Making sense of sound is essential to survival. It is one of our oldest senses. You know, there are mammals who are blind, but they can hear. So evolutionarily, hearing is a very old sense. And, you know, here I am, riding my bike to work. Listen, you can hear my freewheel underfoot, and traffic that's happening a long ways away. It takes a lot of computation, and one of the messages that I have really is that making sense of sound is computationally one of the most difficult jobs that we ask our brain to do, which is why there's so much to work with and why it is really, really fascinating, and we have a tremendous amount of latitude to use this to inform us and to make hearing as good as it can possibly be. So sound is very powerful. It is central to human communication. And sometimes we don't realize how important sound is because sound is invisible. Like many important forces in our lives, like gravity and electricity, magnetism, these are invisible forces, and yet they are mighty forces. So, making sense of sound, of course, is absolutely crucial to how we communicate with each other, how we learn in the classroom. And let me say a few things about making sense of sound and of hearing. Really, we think of hearing as a great big process that involves not only the sound entering the brain, but importantly, there are connections that are informing our hearing system from all the different circuitries in the brain that are important for such things as thinking about the sound, so cognitive, feeling, our reward, and of course our motor system. So, you know, I like to think of hearing as consisting of the intersection of our cognitive, sensory motor, and reward network. So hearing is a great big deal, and it's huge. Now, I want you to listen to this. Tell me if you can hear a sentence. You hear anything? Now listen.
The juice of lemons makes fine punch.
Now listen to the first sentence, please. So, do you believe me? That what we know about sound really influences the way we automatically hear it. So this is part of the cognitive part of hearing. So sound can be both an ally and an enemy, and importantly, it shapes the trajectory of how our brain changes throughout our lives. I like to think of our lives as an evolutionary experiment. And so, it's hard for me to think about evolution in terms of millennia because I deal with milliseconds and microseconds every day. But I can think of a lifetime, and this is really a space for our nervous system to change and to develop. So our life and sound reflects the past. Biologically, our life and sound reflects the past and predicts the future. So it's a form of time travel, if you will. And importantly, the sounds of our lives shape our brains, for better and for worse. So what we can do is we can strengthen our sound processing in the brain through the very best hearing devices, through learning to make music, speaking multiple languages, and we know that there are difficulties that get in the way of our making sense of sound, and that happens as we get older, when we have a hearing loss, noise as a force in our lives, and I'm going to talk about head injury. So first, I want to tell you a little bit about me, and it began with my mommy. So my mommy she was an immigrant and into the United States, and so I lived in a house where multiple languages were spoken. My mother also was a pianist, and one of the favorite places that I had to play was underneath the piano. I would get my toys and things and bring them underneath the piano, and that was where I liked to be. So I think that very early on I had a sense that sound was important. And then as I became a biologist, first I began majoring in comparative literature because I like to read, I knew some languages, but then I took biology as a distribution requirement, and I was hooked. And so my idea, though, is to use the biology that we know to inform sound processing and learning, and especially to use what we can discover as biologists to improve our hearing health. And so I've been chipping away at this for some time. I don't know if any of you recognize this man. This is Raymond Carhart, one of the, really probably the daddy of audiology. And he introduced me to this guy, Peter Dallas, who did a lot of groundbreaking work on the cochlea. And I began, through that introduction, to count hair cells in the cochlea, those 30,000 specialized hair cells in the cochlea. And then I was sticking needles into chinchilla brains and studying something called two-tone suppression in the auditory nerve. And that's where my mommy came in again. So she says, "Nina, what are you doing?" And at that point, I realized that if I was not doing something that my mother could understand, I didn't want to be doing it. So I went from there to putting needles in the auditory cortex of the bunny rabbit, and playing sounds, recording from these individual neurons, but then seeing what happens to the neuron if you make the sound meaningful to the animal. And I was able to witness firsthand the plasticity of the auditory system just from recording the responses of an individual neuron. Yeah, that went fast, didn't it? Woo, look at that. Okay, so beginning, though, in an animal model, and we still have an animal model, my real interest is in humans, but to be able to have the same kind of granularity and control and precision that you have in animal models, but to apply that to humans. That is what is important to me. And so many experiments later, I think we're kind of at that point. And I will talk to you about the frequency following response, or FFR. And, but historically, the auditory system was very much seen as a bottom-up process, which we know now, the idea of an efferent system has become, we certainly have had a paradigm shift in that regard. And a very important experiment was one that Ravi Krishnan did that really made a big impression on me. What he noticed was that if you were a speaker of a tonal language, your brain's response through the FFR, your brain's response to sound automatically picked up on the nuances of changes in tones that happen within a syllable, because that carries meaning in a tonal language. And even when these speakers were asleep, their brains automatically, that became their default network because of their life in sound. So that, to me, was a very important idea. And, so it made it very clear to me that the FFR would reflect the cognitive, sensory, and reward system that our hearing is. So this is me, and I'm very happy because we have this thing now called the frequency following response that can give us a lot of information about making sense of sound. So, we study signals, and I love signals, even though I'm studying very complicated ideas, abstract ideas of how do we make sense of sound, why does music move us so, but we do it with signals. And so the signals are, they're wonderful because they are objective. And 1 and 1 is 2 today, 1 and 1 I can count on it being 2 tomorrow, and I can look at signals such as sound waves and brain waves. I'm looking at the movement of molecules and of electricity, and I really can make computations that are ironclad in their precision. So if you think about the attributes of a seen object, anything, you can feel it, it has a texture, it has a shape. So these are a number of attributes of a seen object, and vision is right in front of you, and it's not a surprise that there was at the NIH, at the National Institutes of Health, a center, an institute for vision, years before there was one for hearing. Because the obviousness of vision is really different from, in sound, there are just as many attributes, but they are much more abstract. And, sound by definition is movement. It's movement of air. And so it doesn't stand still. You can't hold it. And of course I said that it's invisible. But the fact is that there are just as many attributes, there's pitch, timing, timbre, phase. There are so many aspects, as many as there are in vision, in the auditory system that we need to be able to access and understand how the brain processes these things. And so what we can do is, I think I want to go here first, is look at, if we record the brain's response to sound out of a single brain wave, what we can do is see how the brain processes the fundamental frequencies, the harmonics, the timing, how stable the response is from trial to trial. These are just a number of things that the brain can make sense of. And so we can look at expertise, and we can look at disorder, but importantly, I use a mixing board as an analogy here because First of all, each individual has their own way of making sense of sound because of their life in sound. And also, these different aspects of sound processing in the brain are independent, and yes, they also work together, but they give us tremendous granularity. So we're not looking at a volume knob effect. We're really looking at individual components. You can just imagine how important it is to know these individual components when you are thinking about designing and fitting a hearing aid. So here are some of the responses in a little bit more detail. This is the strength of the fundamental frequency, important for pitch, of course, the harmonics. We look at timing, especially timing in speech of the format transitions. The timing in noise, which gets disrupted. We see how well the stimulus and the response compare. So the response is so much like the stimulus that a stimulus to response correlation is possible. And we see how stable is the response from trial to trial. I want to tell you a little bit about the FFR in terms of its terminology, because it's had a bit of an identity crisis. So the FFR, the term, was first discovered decades ago as a measure of low-frequency hearing. And we first used it in my lab at the turn of the century as a measure of processing complex sounds like speech and music. But at that time, I had the idea of calling it CABR, ABR to complex sounds. And as many things in my life, I have grown to regret what I have done. It's just constant punishing. Oh, you could have done that better. What were you thinking? So this B in brainstem is exactly the wrong idea. I mean, for this crowd, you can understand you'll have the context of the auditory brainstem response, but for most people, they don't have that. And even for this crowd, the first thing you think about, ABR, is this kind of low-level signal processing, which is not what the FFR is. Only it is this tremendously complicated snapshot of our life and sound that reflects cognitive, sensory, and reward processes. So I have come to the idea that the terminology FFR, frequency following response, is a good umbrella term for the various aspects of looking at sound processing to complex sounds. So the FFR is objective, it's well vetted, it's mobile, it's fast, repeatable, and it's uniform. We can use the same measure in a newborn baby. I do see that this is the future of newborn hearing screening for how good a child not only can detect the sound, but is he at risk for difficulties making sense of sound. And you can use the same response in an older person, in an animal model. Okay, so now I've got to back up a little bit and show you this, because this is very amazing. So here is a sound wave, and here is a brain wave. What you can see right away is that the brain wave actually physically resembles the sound wave. I mean, this is crazy. As a biologist, recording from single neurons, recording various cortical responses, I've done this, we continue to do this. Usually, the electricity that you get is a very abstract representation of the acoustics, the sound that you present. But here, the sound wave and the brain wave actually physically resemble each other. Moreover, what you can do is you can take the brain wave, its electricity, in the same way as I can take the electrical signal that I can generate for my electric guitar, and my pickups pick it up, and I put it through a speaker, and I can sonify the movement of the strings, right? Well, so I can sonify that electricity. So here's the sound wave, and here's the brain wave. Here's Some more examples.
Stop. Stop.
A scale and the brain's response to the scale. Some Mozart, and then the brain takes over. And my favorite. You know it's coming. Okay, so the fact is, we have a lot to work with. Okay, so we can use all of this information that we can capture from individual people with just a couple of scalp electrodes, and we can start looking at different ways that sound processing in the brain is strengthened and blunted. And one of the forces in our lives is noise. Now, the noise that I'm talking about, noise comes from the word nausea, kind of a seasickness. It also means quarreling. So, noise is just not a great thing. And the noise that I want to talk about is not the noise that you all know. You all know that loud sounds will injure your cochlea. I'm not talking about that. I'm talking about moderate level, safe sounds that are part of our daily lives, just part of the traffic. I mean, how many of you came over here in an airplane? How many of you were using ear protection? That's many, many, many hours of meaningless sound. So, again, because sound is invisible, we don't realize what an incredible impact it can have on who we become. Because biologically, we are what we do. So, we do know that outside of hearing, noise, and this is moderate levels of noise, they impede our health. So we know that if you live in a noisy environment, it increases your stress. How many of you realize, when you are in the kitchen, for example, and the refrigerator turns off, you usually hear that 60 cycle, and then it turns off, and automatically we go, oh. It is such a pleasure, and it is so rare to really have silence. And it is so important for our health, and we don't even realize just the constant, at Northwestern, they're building a new building everywhere, and there's just constant noise, the beeping of the trucks, and we, I don't really think about it, but I know it's adding to how nasty I am. It can disrupt your sleep, it can give you hypertension, endocrine disruption, and importantly, there have been a number of studies showing reduced productivity, learning, development, and cognition. That's important. Noise, background noise will influence your behavior on a task. So this is just a tracking a task with a mouse. And if there's background noise, you're going to make more mistakes. Can't find my little pointer. Anyway, that big red star is there to draw your attention to it. But noise reduces your performance on a simple task like this. This is it's a pretty easy task. But importantly, really importantly, and especially in developing animals, what we know is that animals that are reared in low levels of noise, white noise, have brains that are blunted with respect to, for example, that beautiful tonotopic organization that we know our brain has. And that's because especially the developing brain, but the brain is always searching for meaning. And if you have a developing system, kids can't help but learn languages that they hear. Now, they're asleep, they're trying to make sense of sound, and there's sound that's meaningless, and so their nervous system is going to reorganize or organize according to this meaninglessness. And yet parents are using these noisemakers to kind of keep their kids sleeping better. That's just something to think about. We also know that auditory enrichment is really good. So again, this is work in animal models where you see the normal tonotopic organization in the auditory cortex and single neurons. This is a noise-exposed animal that has gotten this moderate level noise continuously for a while. And after the animal is allowed to recover, if the animal is put into an environment that has an interesting soundscape, the animal is more likely to recover, or it never fully recovers, but it recovers better than an animal that is then raised in complete silence. So it's this ability to make sense of sound actively that is absolutely essential for tuning our brains. So before you put a hearing aid on, or after you put a hearing aid on, you're putting it on a brain that has been tuned for better and for worse. Okay, so let's talk about hearing and noise. So first of all, we have this FFR. Is there a relationship between hearing and noise and the FFR? Well, the short answer is yes, but let me show you what it is. So it turns out that the fundamental frequency, and you can imagine this, the fundamental frequency tracks very well with hearing, speech, and noise. Now, so think about, the fundamental frequency is what determines the pitch of one's voice, the pitch of really any object that helps you track that object, identify that object when there are other sounds in the soundscape. So it would make sense that the fundamental frequency would be an important cue for hearing and noise. And this is something that has been shown across the lifespan. We also know, so remember I told you that the stimulus and that the response that we get from the brain is so similar to the stimulus that a stimulus to response correlation is actually a meaningful measure. So if I correlate two responses, what kind of a value am I going to get? One shadows the other, but it's going to be a number between what? 0 and 1. And, I mean, it's that simple. You do a stimulus to response correlation, you get one number. That's pretty easy to compute. So you can look at the stimulus to response correlation, and again, there is a very nice relationship between hearing and noise. And hearing and noise, I mean by the standardized tests that we have, things like sentences and noise, so hint and quicksyn, which are not the best measures in the world, but they're standardized and that's what we have. But these are what relate to these FFR measures. The other is timing, and especially timing in the formant transitions. So the timing at the beginning of a consonant that distinguishes a ba, a da, and a ga. That kind of timing information is what tracks with hearing and noise. So you have these three things, and they track all together. So this is all the converging evidence. They track objectively with the frequency following response. And we see this at different ages. So we have, you're empowered with a measure that enables you to look objectively at a person's ability to hear a noise. This is really a powerful thing. So we wanted to have a sense of, if you have a normal audiogram, and you're all familiar with the case of you have two people with normal audiograms. One person has a good time hearing a noise, the other person has much, much more difficulty. Why is that? could we see that there is something in the brain, something in the FFR, that is distinguishing one and the other? So these are people who are audiologically normal. They have normal audioacoustic emissions. They also have normal audiograms in the high frequencies, okay, and the ultra-high frequencies. And so here are the guys. There we go. So down is better. The excellent performers, the poor performers, and you can see that the excellent performers just have responses that are larger and more detailed. But let's look at this in a little more detail. You can take any wave in the time domain and do a Fourier analysis and look at the frequency domain. And now you can see that the FFR is reduced in the individuals who have poor hearing and noise. We can do our stimulus to response correlation. And again, the stimulus to response in quiet and, this is the response in quiet to the response in noise. So in the same way as you do a stimulus to response correlation, you can take the response in quiet and compare and look to see how much the response has been degraded once you put noise in there. So has the noise degraded the response a lot? And again, you can see that the people who are good at hearing a noise, the noise has not degraded the response very much. But look, in the guys who have poor hearing and noise, you can see that there's a great big difference. The noise has really degraded their brain's default automatic ability to process signals and noise. The other thing that I told you we look at is timing, right? So we know that anytime you deliver sounds with background noise, it changes the timing of the response. And what we were able to see is that the people who have excellent hearing and noise have less of a timing shift than the folks who have poor hearing and noise. So again, this is a way that we can see that our hearing in noise tracks with how the brain is processing sound. Again, very, very objectively in people. These are people who have normal audiologic measures, but they differ with respect to their hearing and noise. And the guys with average hearing fell very nicely, mercifully in the middle. And also when we looked at cognitive processing, the folks who had better hearing and noise were better at memory tasks. And they were matched. Their visual processing was the same. There was no difference between the groups. Okay? Okay. So, why am I talking about concussion? So, talked about making sense of sound is one of the most computationally difficult things that we ask our brain to do. So if you get hit in the head, that is likely to disrupt that processing. When I was making the comparison between vision and hearing, one of the comparisons that I didn't make is how much faster hearing is than vision. So hearing happens, you can see an action potential every 1 millisecond, every millisecond. With vision, just for an action potential to be occurring, it's 40 times slower. Okay? Now, if we watch these two happening together, you can see that the sound, processing sound, is a very, very, because the information for sound happens in time, it makes a lot of sense that sound processing in the brain would be linked to time. Just to be able to tell the difference between sound that is coming from our two ears, we have computations that are occurring even less than a millisecond. So this is fractions of milliseconds. We have these coincidence detectors that enable us to make sense of sound. So this is enormously fast computation, and again, you can see why it might be disrupted if you're going to get hit in the head. Now, one of the reasons that I'm bringing this up here at this conference is that hearing and noise is one of the difficulties that people have when they have had a concussion. Not only acutely, but even in people who have continuous difficulty after they have had a concussion for weeks, sometimes years. Making sense of sound is a problem. So in a first study, what we did is we looked at kids who had had concussions, and they had concussions from a number of sports: basketball, cheerleading, football, hockey, soccer. And these kids were assessed with the FFR, and we, first of all, wanted to see, is there a relationship between the kids who have had a concussion and hearing and noise? And in fact, we see that very, very clearly. Again, this is Quicksin, and no, actually it's Hint. We see that the concussion kids are performing worse than the control kids. The control kids are athletes that are in the same, they were drawn from the same clinic, but they were there for other sports injuries, like a knee or a shoulder injury. Okay, so they were very, very well matched, these kids. And we already know that hearing and noise tracks with the FFR. I told you that. The real question is this, right? Is there a relationship between the FFR and concussion? And the answer is yes. So really, we have been able to find a marker, a biological marker for concussion that reliably identifies 90% of kids who have had a concussion and clears 95% of people who did not. Importantly, the FFR tracks with concussion severity. So, people have more and less symptoms medically, and the FFR tracks with symptom severity. And it monitors recovery. So again, this is one of the ways that we can use the FFR in many, many facets, but it's really something that you can use in an individual, which is incredibly useful. We've also tested our football players at Northwestern University, all 105 of them. And what we found is that, so we tested them at the beginning of the year, and 25 of them had had a history of a previous concussion. Now, these are athletes that are cleared to play, they are healthy, they're on the team, but they've had a history of a previous concussion. We compared them to position-matched teammates with respect to their FFR, and what we see is, this is a small effect, but we do see that the strength of the fundamental frequency is reduced in the athletes who had a history of previous concussion. So there seems to be a legacy of head injury. And we do know that history of head injury will predispose people to early dementia. So this is an important factor to be thinking about. Also, when we looked at the athletes who did not have a history of concussion, we found it kind of interesting that their FFRs fell below, I mean, it was still normal, but it fell below the 50th percentile. And of course, these are the guys who had a history of concussion. They were quite below. So that really gives us something to think about. Again, this is work that we have to scale and learn much more about. But again, it is a testament to how we're able to use a biological measure of hearing as a measure of brain health, and how brain health often tracks very, very, very strongly with hearing health. So, a few things about what happens as we get older. How can we have the healthiest aging possible? Well, first of all, healthy aging, I think, begins at birth. But, here is our wonderful 104-year-old bike champion. Certainly, it is possible to be extremely healthy as an old person. I want to talk about 3 different forms of strengthening the brain in older adults. One is through computer-based auditory training. The other is what happens if you speak another language. And the third is, what about making music? And again, what I really want you to take away with these is just how malleable our auditory system is. Our hearing is incredibly malleable. So this gives us a lot of, first of all, a lot to work with, but a lot of responsibility, a lot of personal responsibility for what we do in our lives, for how we have our children grow up, for how we deal with our clients who are interested in hearing. So auditory training, we know, changes the way the neurons respond to sound in controlled animal experiments. This is short-term training. But we looked at auditory training in older adults who did the brain fitness program. This is a program that Posit Science puts out. It's the one that Mike Merzenich was behind starting. And this adaptive training is in line with this idea of a cognitive, sensory, motor, and reward framework, because it has increasing memory demands and it changes the dynamics of the signal so that the signal and the memory components become increasingly complex as people go through the training. So what we did is we looked at 75 older adults, and they came to Northwestern University. We measured their FFRs and various other brain responses to sound, and a group went through the brain fitness program for about 2 months, and we had an active control who watched videos, and they needed to they watched videos for the same amount of time, and they needed to answer questions about what they watched, so they were actively engaged with another task. And then they came back to Northwestern. And meanwhile, we had measured a number of aspects of their hearing and their cognition before and after training. So one of the things that we found was that if we looked at their brain's response to sound, what you're seeing here is timing. And the blue line is the control group. So that's the active control group, which you see has not changed. And I see some of you, I'm perfectly happy for people to take pictures, but a lot of this work is published. So you could really look at the details at your leisure. But again, I'm happy for you to take pictures as well. But what we can see is that the group that went through the training, their timing sped up. It got faster. And it got faster not just in general. It got faster specifically for the tricky parts of sound, which is for the consonants. Okay? So also in terms of hearing and noise, we see that after training, the training group got better at standardized measures of, this is Quicksin, of hearing sentences in noise. And working memory improved, and speed of processing improved. Also, the improvements were, with hearing and noise, were greatest for the individuals who had a hearing loss. So this is a very important thing to be thinking about as you're putting hearing aids on people and looking at how they might improve over time together with cognitive training. few things about music. So music and hearing and noise. So as a musician, and by a musician, I'm not talking about professional musicians. I'm talking about people who just consistently play a musical instrument, maybe 20 minutes a few times a week. These are people who have a lot of experience listening to sounds, specific sounds, amidst other sounds. Not that different from trying to hear your friend's voice in a noisy place. And so, our question was, could we see that people who are musicians, who have musical training, would they be better at hearing a noise than people who didn't have that musical training? So, in other words, would the musical training transfer over to speech? And the answer, and we and others have shown this now, is yes, and this is true across the lifespan. That, in these kinds of sentences, which I expect you're familiar with, tell me if you can hear this sentence.
Sugar is very sweet.
Do you get the sentence? Here.
Sugar is very sweet.
Okay, this is the kind of hearing and noise measure that we're asking our participants to do. And again, what is so beautiful is that you can see their brain's responses to sound. You can see that the musician's response in noise is about as good as their response in quiet. So the noise has not had a destructive effect on their default hearing system. This is what their brains have learned to do when they process sound, just automatically. And this is something that, again, it takes time because you have to repeat these sound to meaning pairings. And if you do things again and again, it's like when you learn to drive a stick shift. First you have to pay attention to all the little details. After a while, it becomes automatic. Reverberation, of course, is a problem for hearing in noise. And we know that in terms of the frequency following response, you have a worse response with increased reverberation. Well, that's obvious. But if you're a musician, the effect of reverberation is not as great. This is Beidelman's work. So auditory working memory is also extremely important. As I'm talking to you now, you have to remember what I just said a few seconds ago in order to make sense of what I'm saying. As a musician, when you tune your instrument, you have to remember what it sounds like. You're working your memory. If I'm going to improvise on your musical idea, I have to remember that idea. So again, we know that people with musical experience have better auditory working memory on standardized tests. So this is important, and this is, again, something that you can offer your clients. Play an instrument, and it's wonderful. So with aging, one of the things that happens is that our neural timing slows down. And our neural timing slows down, again, not in a uniform way, but it especially affects our brain's ability to process timing for the very fast information that happens in consonants, for example. So you can see here that the timing is particularly bad for consonants. So if now I'm looking at the response, the timing of an older musician, where do you think their data are going to lie? In between? Here are the data. So you really see that an older musician has a biological response that is much like that of a very young brain. And again, we know that with older folks, as we get older, there's much increased variability. There's a huge variability in performance. Some older adults perform as well as young adults, and some don't. The harmonics is, again, The strength of the harmonics decreases as we get older. If you're an older musician, if we look at the brain's stability, so in other words, if I play a sound and then I play another sound, how stable is your brain's response? One trial to the next. And of course, if you have a very stable response, you have a much clearer representation of what is going on in the auditory world than if you have an unstable response. It's hard to make sense of what's happening. And so here we're looking at trial-to-trial stability. Again, something that is computationally very, very simple. And if you look at an older adult musician, you can see that they have excellent harmonic strength, and they have much better responses in terms of their stability. So what we do really matters, what we do in sound. Neural synchrony, so the ability of neurons to fire in a synchronous manner, is again something that decreases as we get older. But if you look at an older adult musician, you can see that the synchrony is really quite good. So these are kind of spectacular data, I think. And, you know, I didn't do anything, but I'm just showing it to you. You know, it's very objective. So, you know, playing music really does keep your brain young. You know, up on the top there is the response of a typical older adult, and then you can see the response. You can just see it, the brain's response of an older musician is, it just biologically looks very much like what you'd expect in a younger person. So, you know, we know that biological aging begins early, and one way of looking at biological aging is looking at the brain's response to sound, and that's something that begins to change already at age 30. As we know, that's about the time when we start experiencing, some of us, difficulty hearing a noise. Also look at the variability in the older population. So there's a lot of variability, and we can see that this degradation in sound processing is offset by making music. Speaking another language, so, you know, again, we know that cognitive decline occurs as we get older, and, you know, this is largely work of Ellen Bialystok's, showing very nicely that cognition remains stronger in people who speak another language. So this is very important, again, because hearing involves making sense of sound. It engages our cognitive, sensory, motor, and reward systems. And the more languages you speak, the more flexible and strong a system you have. So it's protective. You have strengths in working memory, inhibitory control, that means not paying attention to things that aren't essential, general intelligence, and cognitive reserve. So, you know, with music, certainly, you know, everybody asks me, is it too late? Can I start now? And, you know, first of all, we know that from animal models, animals will continue to change and their nervous system will be malleable until they die. And we know that this is true in humans as well. And there's some very nice data now from a group in Canada showing that a couple of days a week training in, this is in acting, that again involves a lot of learning lines and getting cues from sound, improves listening and noise skills, and again that you can see it reflected in the brain. The brain response changes, and it's so nice to be able to see these objective changes, that often occur well before behaviorally you're able to see that a person's responses to noise, for example, have changed. You know, so like I like to play the piano, and I'll be working on a piece, and it will sound just as bad as it sounded on Monday on Wednesday. So if you are like my poor husband who listens to this every morning, it's like, oh, she isn't learning anything. Why does she bother? He's a musician, by the way. But the fact is, by the time it gets to Thursday or Friday, I am making some progress. But I'm sure that if biologically you were measuring my response to sound and the changes that were happening in my nervous system already on Wednesday, even though you're not hearing any change, any learning, you're not seeing the evidence of learning, the brain is changing. And the brain's changes have to occur before you can see changes in performance. And so this is very important, I think, for feedback to give to your clients as they're getting used to a hearing aid, for example. So let's get to biologically informing hearing health. So we know that hearing loss can influence our cognitive health. So this is Frank Lin's work. And it really makes a lot of sense that if you're not hearing well, you're not going to be able to think well. And again, a visual analogy to me is helpful. How many of you wear contact lenses? And how many of you put them in immediately in the morning? Or give me a show of hands for how many of you wait a while before you're putting them in. Everybody sticks them in right away. All right, so that's not going to help me one bit. Me, on the other hand, so I often walk around without my contact lenses for a while in the morning, have my breakfast, my coffee, and then, and I realize, even if I have to get on a phone call, that if I need to think, I should put my contact lenses in, because being able to see better makes me think better. And I think that the same is true for hearing. But again, with the vision, it's very, very clear, oh yeah, I can read that text, or no, I can't read that text. With hearing, it's so much more subtle that you don't realize, you're losing your hearing, you're not thinking as well. But this is a really, really, really big deal. And again, it's just strengthening this idea that hearing involves how we think and how we feel about sound. So we know that hearing a noise reflects cognitive health. We know that working memory is better as our hearing a noise is better. And again, this is the situation where you have two people who have identical audiograms. One person is good at hearing a noise and the other person is poor. And people call it hidden hearing loss. I think it's not so hidden if someone is really having difficulty hearing a noise. But again, it's very beautiful to see in the biological response, and it's also very comforting for the person to be able to say, well, yeah, okay, I can see that your audiogram is showing normal hearing. They're complaining that they have difficulty hearing a noise. Now, if you can say, well, biologically, we can see that there are some bottlenecks, and maybe we can strengthen them. This, I think, is very, very telling. So again, you have a non-musician with normal audiogram, and you have a musician who has a typical presbycusic hearing loss. And what is rather stunning is the fact that the musician, even though he has a hearing loss, has better hearing and noise abilities than an age-matched non-musician with normal hearing. So, what is that telling us? That's telling us that this repeated sound to meaning connection that happens as you play a musical instrument and as you resolve the physical complexities of playing this instrument, this is something that is very, very important and strengthens your ability to make sense of the auditory world. And again, you can see it very nicely in the frequency following response, where, well, here is the non-musician, the response in quiet, the response in noise, clearly depressed, and here is the musician with the worst peripheral hearing, and you can see that the response in noise is very strong. That's the fundamental frequency. Auditory working memory, again. So we're looking at auditory working memory. You know, by auditory working memory, the way that we test it is I'll give you the names of a couple of items and some nouns, and then I'll ask you, tell me, remember please, the nouns that I just said that were names of flowers that begin with the letter P. So you have to think, okay, well, what did she say? What were the words? Which ones were flowers? Which ones start with P? That's your working memory. And your ability to hold that working memory, if your auditory representations of sound are strong, you will be able to hold that information in your memory in a much more efficient way. And if you are a musician who has constantly strengthened their auditory working memory, you have a system that is going to be very helpful for making sense of sound, whether the sound be music or speech. So, how about hearing aid and device fitting? You know, we really think that this can be informed by biology. So, you know, here we have a hearing setting, and this is the time domain, this is the frequency domain, and someone comes in to the clinic and they say, well, you know, this hearing aid is not working anymore, and they are fit with a different hearing aid. And, you know, they wear it for a while, and they're pretty happy with it. You know, I can't remember the last time I heard so well, so, you know, you have some behavioral confirmation. But you can also see very, very clearly that the response, both in the time and in the frequency domain, and especially you can see the strength of the fundamental frequency, you can see that this is something that is simply strengthened in an individual who is wearing a device, either a better device or a device that's better fit. And this kind of feedback, to me, is what I think will be the current, and if not the current, but the future standard of care. Because again, each person has a different life in sound, is going to be affected by a hearing aid device and settings differently, and is also going to be affected by the experience of wearing that device over time. And so in terms of, you know, one thing is the initial fitting, but beyond that, you want to do fine tuning, and there's a lot of tuning that can be done once if you have particular parameters to look at after someone has worn the device for a while. This is Samira Anderson, and she was an audiologist for about 20 years before she got a PhD in neuroscience in my lab, and now she is at the University of Maryland, and she is doing a lot of work on the biological information of hearing through hearing aid devices. And so this is some of her data where you can see unaided responses, and then with the aided response, you can just see that the hearing aid is boosting neural synchrony. And, you know, that's a very clear, objective indication that not only the amplification is helping, but again, I think that if you can arbitrate among different settings and different processing strategies, you know, this is something that you can see objectively, and you can get information back that can inform your best practices. So when I was at the ARO meeting, Ludovic Bellier presented. He's from France, and he is also doing some work on the FFR and hearing aids. And so, these are people to watch. So what I can envision is some automated fitting. Imagine if you can be recording rapidly FFRs to dozens of algorithms to find which is the best fit for a particular brain. So you can just do this very quickly and be able to then determine, oh yeah, that's the one. So this is what I am envisioning. I also think in terms of training strategies. What is the best strategy for an individual person? There are a number of strategies, and there are many others. One person compared to another person might benefit from a different hearing strategy. And again, this is to choose the best strategy, or at least to make a first start at a best hearing training strategy is something that can be informed by biology. So there are a number of ways of strengthening sound processing in the brain, and I think that you are probably most interested in what can we do with devices such as cochlear implants and hearing aids and FM systems. It's really quite interesting in people who have normal hearing peripherally, they have normal hearing thresholds, and yet have difficulty processing sound. This is not only for kids with auditory processing problems, but even with older adults. I am hearing from my audiology colleagues that wearing a low gain amplification can help. Because what it does is it helps you pay attention to what is important. And you have to learn how to pay attention to the sounds to strengthen those circuits. And especially if you've lost some hearing, you have to relearn those cues. An example is, I play a little guitar. And I mentioned my husband's a musician. So the other day, I'm trying to learn this Dire Straits lead, and he comes by and he says, "Nina, if you would just listen, you would hear that when he's playing those 5 notes very, very rapidly, he's not picking the individual strings note for note, he's pulling off the strings with his left hand. And so it has a very distinctive sound. And once he told me what to pay attention to, I had been deaf to that. But once I learned what to pay attention to, I get that now. Now when I hear that sound, it's, oh yeah, I know what to do. But you have to learn how to pay attention. You have to know what it is that you have to pay attention to, and sometimes these low amplification hearing devices can help people make sense. And also this is something that we have learned with FM systems, especially in kids who have auditory processing and language development problems. Successful courses of actions is software-based training, music training, and these are a couple of articles that I suggest that you start, use as starting places. And then finally, this focusing of auditory attention through FM listening devices in the classroom. What we were able to do is a study where kids who had, these were all really smart kids who had especially language and reading problems. And they went to a special school that had all the technologies available, and they wore an FM system in the classroom. Some of them did, and some did not. They were educated in the same classroom. And the kids who wore the device, their reading and language skills improved more than the kids who did not wear the device. And interestingly, we could have predicted ahead of time who was going to benefit, because we could see in their FFR, some of the kids really had a bottleneck in how stably or unstably the brain was processing sound before the device. After they wore the device for a year, again, once they learned what to pay attention to, which was the teacher's voice, automatically, when we measured their brain's response to sound a year later without the device, their brain's responses to sound were more stable. Okay? So, in terms of hearing health management, here is our little vision. We call, my lab, we call ourselves Brain Volts. We're at Brain Volts on Twitter. But there are 3 questions that one asks, I think. One is sound getting in? How well does a listener use sound? And how well is sound processed by the brain? I think this is information that we can capture. So is sound getting in? Well, that's going to be conventional audiometry. And you tell me what the best convention audiometry is. You know that. But how well does a listener use sound? Again, I think that we need to be considering speech and noise. And I know that a lot of standard audiologic evals do not include speech and noise, at least not sentences and noise. And that to me is, it's baffling. But I also, this is my opportunity to say, our current measures of hearing sentences and noise are really not as strong as they could be. Our field really needs good measures of hearing, speech, and noise, especially for people who have pretty good hearing thresholds. I mean, because where we have difficulty is when there is all kinds of confusing background noise. It can be traffic, it can be reverberation, it can be other people talking the same language, different languages. There are so many nuances to hearing and noise, and there need to be good, granular measures. I mean, the measures that exist now are, okay for people who have pretty severe hearing loss, to see if there has been a change with a hearing aid or whatever. But we really need stronger measures, I think. So I'm hoping that some of you will develop those. I think that we need to look at auditory working memory, and we need to look at measures of attention, and these are some of the standardized measures that we like to use in the lab. And I think that's very, very important if you're going to be thinking about hearing, to know, are there strengths or bottlenecks in how a person is using sound? And then, of course, how well is sound processed by the brain? For the first time, we really have a very granular measure of sound processing in the brain. And I think it behooves us to use it. We recently put together a volume on the frequency following response that I hope will be of use to you. And I also want to point you to, every month or two, we write this little couple paragraphs for the Hearing Journal and for the Hearing Matters column. And if you go to our magical website, under publications, there is a little tab on the top that says for clinicians, and it will take you to these Hearing Journal entries. They're all in one place, and you may find that there are entries that interest you. So, again, if you don't want to read a whole big long article, you can just get a snapshot of what we're thinking and what research is showing about different aspects of hearing, and then if you're more interested in that topic, you can download publications and go from there. Okay, so I'm going to sum things up here. So the sounds of our lives shape how we hear, for better and for worse. The FFR is an index of cognitive hearing health. And importantly, it tracks with hearing and noise. And I think what is very important to be thinking about is how we can harness the biology to inform our development of hearing aids, strategies, fitting, to follow people in terms of not only fitting them, but to follow their management and care. I really do think that the standard of care for hearing assessment, intervention, and instrumentation should be informed. I mean, knowledge is empowering. It should be informed by the biology. So, what next? So we want to be able to inform hearing health through the biology. And again, one of the things that excites me about the frequency following response is the fact that it is so meaningful in individual people. In fact, it is more meaningful in an individual than in groups. And most of the biological measures that we have are really informative when you're looking at a group of these people and a group of those people. But when you want something for an individual person, the FFR is really useful. So it can give you a personalized biological outcome. And the way forward, I think, is to develop a standardized, user-friendly way of recording these responses. Currently it's expensive and it's often complicated to get these responses. And I'm hoping that we can develop a user-friendly platform. I founded a company to try to develop this. I have since resigned from the company just because running a company and running a lab is just a lot of too much work, and I feel like I need to put all of my attention into running the lab, but I am consulting for them, and I want to see them or anybody succeed in bringing, making accessible a user-friendly platform of FFR, but it's currently available anyway, and any system that records electrophysiologic responses. Also, we give away for free our stimuli, our MATLAB routines. Intelligent Hearing Systems has they call it a CABR module because of my idiocy. But again, you guys have the knowledge and the resources to be able to use this biological information right away. Because we want to be able to empower hearing device development, science, and clinicians. These are the folks in my lab who do all the heavy lifting. I really have a marvelous team of people with all different backgrounds. I am just the luckiest scientist. I just can't believe that they pay me to have fun with this crew and to discover together new things. And I want to invite you, please, to visit our magical website. There are cards that I left for anybody who would like to just take away a card that was drawn by one of our students with our website. You'll get it at the at the desk downstairs where you checked in. But if you take a look at all of those different topics, so for example, if you click on hearing and noise, what you'll find is that for each topic we have an overview slideshow. And the slideshow will show you a picture and a line of text that summarizes 2 years of work. And so you can just get a sense, an overview of the different lines of research that we do. And as you're interested in some of the topics, you can go as deep as you want and download the publications. But I suggest that you start there. And also, we have the demonstration of our biological approach. There's a little video right on the home page that you can watch. It's just a minute or two long. And, you know, this climate, in terms of funding, is really, really rough. I mean, right now we are positioned because of, you know, where we have traveled in all these years to make a lot of progress. But you know, I've been funded by the NIH for decades. These dollars are drying up, as you know. We have a donate here button. So we are investigating all forms of, especially more private funding to keep the science going, because it's rough. And you know, this is really what we're looking for. But again, I welcome you to have a look at all the research that we've put together, and that's kind of what I've got for you this morning. Thank you.